Somewhere on chromosome 7, there is a gene that has 6,129 active letters in it. This gene strings together 1,480 amino acids into a protein whose function is to allow salt to penetrate various membranes in the body. Little Susan has a tiny error in that gene in her 7th chromosome. 3 letters are missing, and that causes the protein that Susan's genes manufacture to be ever so slightly misshapen. And although the difference in the shape is tiny, the consequences are huge. This particular protein does its work in the linings of the lungs. By inserting itself into the plasma membrane, the protein makes a passageway for the salts to enter and leave the cells. But if the protein is not exactly the right shape, then it cannot transport the plasma membrane and therefore cannot do its job. Then salt gets trapped inside the cell, and that causes the cell surface to become sticky and covered with thick mucus. This results in wheezing, breathlessness, and the persistent cough to expel troublesome mucus. This is cystic fibrosis, and it is the result of just 3 missing letters on chromosome 7. When genetic diseases run through families, then we know the mutations in the genes that cause these diseases are being inherited. Here is an example. In a normal gene, this is the sequence, ending G, T, A, G, C, A, G, T. But sometimes the gene is missing 2 of the letters. This new configuration is a mutation that can often lead to breast cancer, and it is passed from generation to generation, causing the potential for disease to be passed down as well. How can we fix genes that are broken? Gene therapy is a new and promising technology. Consider a disease like SCID, which is an autoimmune disease caused by a single gene mutation which prevents the body from producing normal disease-fighting cells. These patients have no natural defense and often spend their lives in an isolation bubble to prevent contact with other people. Since bone marrow is the place where cells are made which normally defend the body, bone marrow is drawn from the patient, and a normal gene is inserted into the patient's DNA, either replacing the faulty gene or coexisting with it. Then these repaired marrow cells are placed back into the patient's body, where they begin to multiply and produce normal disease-fighting cells. We are also developing the skills to choose which of our genes our children will receive. Greg and Marie are about to hear the results of their in vitro fertilization from their genetic counselor. They are about to face the full implications of this emergent technology.
Your extracted eggs, Maria, have been genetically matched in vitro with Greg's sperm. Now, you've selected a boy with blue eyes, brown hair, and fair skin. As an adult, he'll be 5 feet 11 inches tall, and his IQ will be near genius level. Now, I've taken the liberty of eliminating a few undesirable traits: alcoholism, cancer, Alzheimer's, baldness, obesity.
Well, I thought certainly no diseases, but...
We were wondering if we shouldn't leave some characteristics to chance.
You want to give your child the best possible start. Remember, this child is still you, simply the best of you. You could conceive naturally 1,000 times and still never get such a result. I'll give you a minute to think about it.
Should we choose the best that's in us for our children?